5 is the idea of electromagnetic radiation. So the idea is energy can travel through space in the form of electromagnetic radiation. And this is going to become important for us as we talk about the atomic structure, and you'll see why. But just some things about electromagnetic radiation. They exhibit wave-like behavior. So you can talk about various types of electromagnetic radiation just like any waves, and you can then characterize them by the wavelength of the particular wave, and that would be the distance between two consecutive peaks. You can talk about the frequency, which is the number of waves passing through a given point per second, and then you can also talk about the energy of the waves. And the thing that we're going to see that's going to be very significant is that light or electromagnetic radiation has wave-like behavior, but it also has particle-like behavior. And this is known as the wave-particle duality of light. So we can talk about light as traveling through space in the form of waves, but you can also talk about it as sort of packets of these particles called photons traveling through space. And you can almost think of the photons sort of traveling in wave-like motion. And so as a result of that, you can talk about the energy of a particular photon of a particular type of electromagnetic radiation. And put here speed of light because all electromagnetic radiation travels at the speed of light in a vacuum. So, all right. So again, this is just a slide showing you the wavelength. What is a wavelength? Distance between two consecutive peaks. And because it's a length, you can talk about it in terms of centimeters, micrometers, meters, nanometers, and so on and so forth. Frequency, again, you have a slide in your notes that talks about it, and it shows you how you can calculate that. Basically, it's a number of cycles that pass through a given point. So the narrower your waves are in terms of being really close to each other, the more cycles you have passing through a given point, and then that means that you're going to have a higher frequency. The broader, the farther apart they are, that means that you're going to have a lower frequency. All right, now these are some pretty important relationships. You've got some equations relating the frequency of a particular wave with the wavelength. So notice here that the wavelength times the frequency is equal to a constant, which is the speed of light. And so you can obviously then, if you know the wavelength of the electromagnetic radiation, figure out its frequency. If you know its frequency, you can figure out the wavelength. And just some note about units here. If the speed of light is in meters per second, then when you're solving for the wavelength, it's going to have units of meter. When you're solving for frequency, it's going to have units of inverse seconds or 1 over seconds, which corresponds to a hertz. And then you can also talk about, again, the energy of the photon, because remember, the electromagnetic radiation is also, or also has particle-like behavior, so you can think of it as a stream of photons traveling in a wave-like manner. And so the energy of each photon can be calculated if you know, for example, the frequency of the radiation, electromagnetic radiation, and you know this constant called Planck's constant, which is going to be given to you 6.6 times 10 to the negative 34 joules times second. So notice here when the frequency is in hertz or 1 over seconds, the seconds will cancel and you'll be left over with an energy in joules. So this is all in the metric system. You can also talk about Planck's constant in other units, but you know we're only going to be sticking to the metric system. And of course, if you look at this first equation, you know that you can rearrange this equation and find that frequency is equal to c divided by lambda. So if you take that expression and plug it in here, you can also express the energy of a photon in terms of the wavelength. A couple of notes here. Notice that the higher the frequency of your electromagnetic radiation, the higher the energy. So if you have two photons and one has a higher frequency, then it's also going to have a higher energy. You can also see there's an inverse relationship between energy and lambda, wavelength. So in general, the shorter the wavelength, the higher the energy is going to be. So shorter wavelength corresponds to higher energy. A longer wavelength, on the other hand, corresponds to a lower energy. So just some relationships you can see here from this equation. All right, and these are the different kinds of electromagnetic radiation that are out there. You know, I'm sure you've heard of gamma rays, X-rays, ultraviolet, infrared, microwaves, and so on. Visible light, of course, is white light, and you can break that down into different colors, colors of the rainbow. So these are the different frequencies, and you can see here again, we can see that gamma rays, because they tend to have the shortest wavelengths, they tend to be the most energetic. They cause, for example, the most damage, whereas radio waves tend to have the longer wavelength, and so they tend to be less energetic. And so you can see the relationship here between energy, frequency, and wavelength. Alright, so we talked about electromagnetic radiation. Again, can behave as waves. So on the next slide, I sort of have this, wave, showing you light as wave, and you can see it's composed of magnetic field, electric field. We're not really going to get into that, but light travels as waves. It also can behave as small particles called photons. So you can talk about energy being transferred in these particles called photons, and this is kind of attempting to show this, the slide right here is attempting to show that, and you can almost imagine photons traveling in wave-like motion. So the photons are sort of going up and down in a wave-like motion. That is a useful analogy to use. And the really nice thing about thinking of electromagnetic radiation as photons is that you have to remember that energy can be transferred or occur only in discrete amounts. So just like matter, you can only talk about 1 or 2 or 3 hydrogen atoms, but not a fraction of an atom. Likewise, when you talk about energy transferred from electromagnetic radiation, it can only be transferred in discrete amounts: 1 photon, 2 photons, 3 photons, and so on. So you can't transfer a fraction of a photon. Okay, and later on in your slides it talks about this equation where there's a difference in energy of some substance, and that's equal to n times Planck's constant times the frequency. And so what that is saying is that you can again transfer only n numbers of photons where n is an integer. So you can't transfer half a photon, and so on. And if you know your electromagnetic radiation that you're dealing with, whether it's infrared or UV or whatnot, if you know the particular wavelength and or the frequency, you can then figure out how much energy is allowed to be transferred using that particular type of electromagnetic radiation. So it can't be a continuous amount. It's just discrete amounts, some number multiple, some number integer multiple of the energy of 1 photon. Okay. So that's kind of the idea here. And we'll see that again when we talk about the atomic structure. That'll be very significant to us. Alright, so this is what I was referring to again. A system can only absorb or transfer energy in whole quanta or packets of energy, and those are basically packets of photons. So either 1 photon, 2 photons, 3 photons, and so on and so forth. Okay, quick note about visible light. We know that it's composed of light of different colors of different wavelengths. So we can separate these colors by a prism, similar to a rainbow you might see after after a rainy day. White light travels through the raindrops, and it also gets separated into the different colors. So these are some wavelengths for the different colors of the rainbow. And if you think of what happens with atoms, if you take an atom and you excite it, so you maybe run an electric current through it, kind of like we have in that little picture on the side, notice here what happens is the electrons in the atom are going to get excited. All right. In the case of hydrogen, if we were to look at the light given off, or the emission, we see a blue light. But if we were to take this blue light and separate it into some colors, we will see this emission spectrum where this color that's emitted is actually composed of red light, sort of a light light, and then there are two sort of violet indigo colors. And so this right here is known as the emission spectrum of hydrogen. And the idea is this. The idea is when you excite the atoms, okay, what you're really doing is exciting the electrons. And you're exciting the electron from low energy level to higher energy level. So you can think of it, these electrons are sitting in these floors, right? There's a first floor, a second floor, a third floor, and so on. Well, in the case of hydrogen, okay, there's only one electron, so it's sitting in the first floor. And when you zap it with an electric current, what happens is that one electron gets excited and goes from first floor, let's say, to second floor, or first floor to third floor, or first floor to fourth floor, and so on. So it gets excited and moves farther away from the nucleus. Again, it makes sense. I mean, if you think of the electron, it's negative. It's attracted to a positively charged nucleus. So in order to get it to go far away from the nucleus, you have to excite it. You have to give it energy for it to be able to overcome that attraction to the nucleus and jump far away. So you're exciting it. You're giving energy, and you're allowing it to have that energy to run away from the attraction of the nucleus and go to a higher energy state. Well, things in nature don't like to be in the higher energy state if they can help it. So as soon as that electron jumps, let's say, to the second energy level, It says, wait a minute, I don't want to be excited. I don't want to have that much energy. I want to relax. I want to give off that excess energy and go back to my, my stable ground state where I'm low energy. I like the first floor the best. So it's going to release some of that energy. And in the case of hydrogen, when it releases some of that energy, some of that energy is released in the form of light that we see as that sort of blue hazy light in that little bulb that you see on the right hand side. Well, if you take that light and you resolve it into its different colors, in the case of visible light, which is the only thing we can see, of course, you see these four distinct colors. And the idea is each one of these colors corresponds to a transition from one of these energy levels, these higher energy levels, to the ground state level, okay, or to another level, okay. And so the idea is you don't see a continuous beam of colors. I mean, you don't see continuous color here. You see just discrete colors of specific wavelengths. So what this tells us is that the um, electron can only occupy certain energy levels. Okay, it can't just occupy any level. So if it goes from, let's say, 3 to 2, you give off one particular energy, a photon of particular energy of particular light. If it goes from 2 to 1, you give off another photon of a particular energy of a particular wavelength. But you don't just give off any random photon, implying that it cannot be just anywhere in that atom or anywhere between those electronic energy levels. So this was really significant. Seeing the line spectrum for hydrogen was really significant because it told us something about the structure of the atom. It told us something about where the electrons can or can't be. All right. So again, this is kind of the idea here that I just said. Again, when the electron is excited, it absorbs the energy and it jumps to a higher energy level. And when it relaxes, it releases energy, and the energy it releases, or the photon of energy it releases, corresponds to the difference in the energy between those levels that it had just gone from and to. So if it's going from 3 to 2, energy level 3 to energy level 2, it's releasing a photon of light or a photon of energy that corresponds to the difference in energy between level 3 and level 2. And if in this case if you were to have a continuous like a ramp almost, as opposed to stairs, a ramp where the electron can be anywhere, you can imagine you can produce an infinite number of photons of different energies, and therefore you'd see a whole bunch of colors on your spectrum. But since you have these specific energy levels that the electron can occupy, almost like steps, you can only give off a photon that has energy corresponding to the difference between those two specific steps. Okay, it's not anything that you please. It has to be specific levels. So that's kind of the idea behind line spectra, and why they were so significant. When we first saw them, they were very significant because they gave us some information about the structure of an atom. What are these electrons doing? Okay, what energies do they have? So, so that gave rise to the Bohr model. So the Bohr model, of course, is incorrect. We don't use the Bohr model at all today. But historically, it was very significant because it was the first time that someone, again, came up with that proposal that electrons occupied these specific energy levels. So the idea behind the Bohr model that Niels Bohr developed specifically for the hydrogen atom was that you had, of course, the nucleus in the middle. So you've got this, dense positive center, and you've got these orbits, if you will, and literally they're circular orbits where the electron is allowed to stay, and it's only allowed to stay in these specific energy levels or these specific orbits. And so the electron could kind of orbit the nucleus in n equals 1, so that first circle, or it could orbit the nucleus in n equals 2, or it can orbit the nucleus in n equals 3, and so on and so forth. And that's it. So it can't be between 1 and 2, for example. It can't be in that little space between circle 1 and circle 2. It can only be here, it can only be here. Again, analogy to that is think of steps. You can only be on step 1, step 2, step 3, or in a house, you can only be on the first floor, second floor, third floor. You can't be like, floating midway. And that was the idea behind the Bohr model. So in this case, if I have, again, the atom and I excite it, so maybe I run an electric current through it like we had in that little light in that little bulb, then you're going to excite the electron. And so suppose it were n equals 1 initially, perhaps it would jump to n equals 2. Once it has that extra energy, it can detach itself or overcome the attraction to the nucleus and jump to energy level number 2. But of course, as soon as it does that, it says, wait a minute, I don't like having that much energy. I like to be low energy. So it says, well, I'm going to release the energy, emit that energy. So it emits it off and gives it off. And if we're lucky, it's going to emit it off in a photon of visible light. Of course, a photon can be given off in any range in that electromagnetic radiation, but in terms of what we can see, we can only see visible light. So if we're talking about the line spectrum, those colors, those would be photons given off that correspond to energies or photons of energies for the visible light region. Okay, so that's kind of the idea behind the Moore model. So you've got these specific energy levels where the electron can reside, and you can only give off the photons that correspond to the difference in energy between these levels, not just any random photon can be given off. Okay, and this is just an energy diagram showing you that. So n equals 1 would be the lowest energy closest to the nucleus, n equals 2 would be farther out, n equals 3 farther out, and so on. Just a little thing about the Bohr model, not really a huge deal, but as you get farther and farther away, the energy levels actually get closer and closer and closer. So not really a huge deal, but you will see that with the equation. If you plug in numbers, you'll see that the energy difference actually gets smaller as you get farther and farther away from the nucleus. So, but that's really just a minute point. Okay, so that's again showing you that. And this diagram, it's similar to the first one on the previous slide, but this one actually shows you the different colors that showed up on the hydrogen spectrum, on the hydrogen line spectrum, and what these colors corresponded to in terms of transition. So you could see that, that red color that we saw corresponds to the n equals 2 to n equals 1 transition. And this one corresponds to the n equals 3 to the n equals 1. And this one corresponds to the n equals 4 to the n equals 1. So you can see here again, specific photons are given off, not just any random photon, and they just match perfectly with the energy difference between these energy levels that Bohr came up with. Again, you don't see a photon given off, that corresponds to the energy between this point in the middle, let's say between energy level 2 and energy level 3 to energy level 1. You can't have that electron be in the middle. And again, it's supported by experiment because we don't see a color that corresponds to the energy difference here to here. So only from this energy level to another energy level, specific energy levels are allowed for the electron, not just any random one. Otherwise, you'd see a continuous color on your line spectrum. All right, and of course there's always some numbers, to back up observations. So Bohr came up with these formulas that just matched perfectly with what we saw for the hydrogen atom. So he came up with this equation, and this first one basically tells you the energy at a particular energy level n. So if you have n equals 1, which would be that first energy level that's closest to the nucleus, so that n equals 1, if you were trying to figure out, okay, what energy does the electron have at n equals 1, all you have to do is use this equation, and you can plug in n equals 1, and z here stands for the nuclear charge, and the nuclear charge basically is how many protons are in your nucleus. So for hydrogen it's just a 1 because there's just one proton in the hydrogen atom. So you plug that in, and you you multiply this number that we just called the Rydberg constant times in this case just 1 because you've got 1 over 1, and you get the energy level, the energy for n equals 1. And you can do some calculations. For example, I did here for n equals 6. What do you have? And you just again plug in whatever n value you're looking at. So right here it would be n is 6, so that would be 1 over 36, and then multiply that by the Rydberg constant. Okay, so that's pretty much just for figuring out the energy at a particular energy level. Now, most of the time we're interested in the energy difference between energy levels because that's what we can see or observe experimentally. So if I take hydrogen and I excite it with electricity, let's say, and I want to know what energy is given off, I can see that experimentally by looking at the colors that on the light spectrum, right? The photons of color that appear on the light spectrum. So I can then kind of confirm that experimentally. So we're more interested in the energy differences between the energy levels because that corresponds to the energy of the photon that's released that I can see on that line spectrum. So then we basically re-express or rewrite the equation in a different form to show us the energy difference. Okay, so basically you take energy at n, whatever you want, minus the energy at n, whatever you're ending up at, or actually the final minus the initial, so it'd be En final minus En initial, and if you take those and you plug them in, plug the expressions in that you have on the previous slide here, you will come up with this rearranged form. So what it is basically is the Rydberg constant multiplied by 1 over n final squared minus 1 over n initial squared. Notice I took out the z here. The z is just 1, again, for hydrogen. If you were trying to write this equation for helium, let's say, or some other element, you would have to make sure that z stays in there. So for helium, for example, it would be a 2 up on top squared, and so that would be a 4 up on top. If it's hydrogen, it's just 1 squared, and so that would just be 1. So for hydrogen, it's the simplest that you can have. Okay, and so using this equation, then we can calculate the energy difference between specific energy levels. Okay, and that again correlates directly to what we see experimentally in the case of hydrogen and its 4 colors that appear on the line spectrum in the visible region. So this is an example of how you'd apply this equation. So let's calculate the wavelength of the photon emitted for the n equals 2 to n equals 1 electronic transition. So when the electron goes from the n equals 2, which is higher energy, to n equals 1, which is lower energy, in this case it's the ground state for hydrogen, for the electron in hydrogen, then all you have to do is basically apply that equation. So again, we've got the Rydberg constant, we've got the n final minus the n initial, and so the final here would be just 1 over 1 squared. Initial would be 2, so that's 1 over 2 squared, or 1 over 4. So you're essentially getting 1 minus 0.25. So it gives you a positive number in the parentheses, or 0.75. You take the 0.75, multiply it by the Rydberg constant, and you get 1.63 times 10 to the negative 18 joules. But something to notice about this is that you've got a negative sign on your delta E. So by convention in chemistry, if you ever see a change in energy that's a negative, has a negative sign, that implies that energy is released. So notice here, I mean, the question had said, calculate the wavelength of the photon emitted. So I told you that there was a photon that's going to be emitted. But if you had no idea, if you were clueless, you didn't know whether, energy should be emitted or absorbed in this transition, calculating the delta E and coming up with a negative sign, automatically that negative sign says, hey, energy is released. So anytime you see delta E is negative, that means the system is losing energy. And so energy is being released, in this case, from the hydrogen atom, which makes sense, again, because it's going from a higher energy level 2 to a lower energy or a less energetic state, n equals 1. So, all right, and so to answer the question, then the photon of light released would have energy equals to that, which if we wanted to know what the wavelength was, we can just remember, equate it to the hc over lambda equation that we had earlier in the slide, and solve for the wavelength, and then therefore figure out what color that corresponds to. So we can do that. All right, and that's pretty much it. This is the same thing over here. This says calculate the wavelength of the photon emitted for the n equals 3 to n equals 2 electronic transition. And we can see here again, we plug in the equation, plug in the final, which is n equals 2 in this case, and the initial, which is n equals 3. And again, if we do the math, we come up with a negative change in energy, which again implies that energy here is being released. So energy is being released. Again, you're going from a high energy state to a lower energy state, n equals 2. All right, and again, we can go through and calculate lambda and figure out what wavelength of light that corresponds to. In other words, what photon we should be seeing on the line spectrum that corresponds to that. And by the way, these equations are going to be given to you on the exam, so you don't have to memorize them at all. So those will be given to you guys on the exam. All constants will be given to you guys on the exam as well. So you just have to be able to use the formula. So the Bohr model, your book, of course, does a lengthy discussion of this, but the Bohr model worked really, really nice for hydrogen. I mean, it just worked wonderfully. It explained the colors that we saw on the line spectrum, made sense. Everything was wonderful about it. However, the problem with the Bohr model is that when you started to apply it to helium, some corrections had to be made, some modifications had to be made. And then lithium, boy, was that even worse. So once you started applying it to more complex or multi-electron systems, it just kind of fell apart. It didn't work anymore. First they started making slight modifications, just kind of fix it, kind of like fudge factors, and then it just started deteriorating. It was just not good anymore. I mean, it just didn't apply at all. So what they said then was, okay, well, this can't be true. Remember, a model has to reflect reality, or has to at least be able to predict correctly what we're going to see. Well, the Bohr model wasn't able to do that. So there was something fundamentally wrong with the Bohr model. And of course, we have a current model of the atom, which is known as the quantum mechanical model, and that's going to be discussed in part 2. But the quantum mechanical model is completely different in the sense that, first of all, the electrons don't move around the nucleus in these circular orbits. So we don't talk about orbits, we don't talk about the electron moving in these fixed paths. That's totally wrong. It's totally erroneous. So unlike, the Bohr model, or where you can kind of think of the electrons as these planets moving in these fixed orbits, um, in reality, the model we have today of the electron is completely different. We don't have them moving around in fixed paths and circular orbits around the nucleus. But the Bohr model was very important historically, and so we still teach it. Why? Because it really explains the idea. Whoops! It really explains the idea the idea that electrons occupy specific energy levels really nicely in a very simplistic way. And we'll see that that's also true of our quantum mechanical model, in that we believe that electrons are only allowed to reside in specific energy levels. An electron can't be anywhere, if you will, have any energy. There are only specific energy levels or energy quantities that are allowed for the electron. And so that's really the significance of the Bohr model, is it was the first one of its kind to come up with this notion that only specific energy levels are allowed for electrons, and that energy can only be transferred in particular packets to the electron, corresponding to these differences in the energy levels. So, all right. Now, with the other thing that you guys will see in this chapter, or if you haven't already seen it, is this whole idea that not only is electromagnetic radiation or light have particle-like behavior, but we can also do it the other way. We can also say that matter or particles, that we think of as matter, so atoms and so on, electrons, have wave-like behavior. So it's kind of a two-way street. Electromagnetic radiation or light has wave-like behavior, but it also has particle behavior, and particle behavior, particles or matter also has wave-like behavior. So it's kind of a two-way street here. And so the de Broglie equation attempts to calculate a wavelength for a particular substance, having a particular speed, velocity. And in this case, we can pretty much put in anything. So anything that has a mass to it, which would be matter, anything that has mass to it, and somehow is traveling at a particular velocity, we can calculate what wavelength is going to be associated with that motion. So how is that particle going to travel in a wave-like motion? What is that wavelength of that wave in which it travels like? And here h stands for Planck's constant again, which we've seen before. And just a quick note about units, notice here lambda would be meters. If you plug in your velocity in meters per second, Planck's is in joules, your mass is in kilograms, your lambda is going to come out in meters. So this one example shows that if you have an electron and if you have a ball, okay, and you've got, both of these are particles, and the question is, what is the wavelength associated with the electron? Because we just finished saying that matter has wave-like behavior, wave-like properties. And so what is the wavelength for the motion of an electron? What is the wavelength for the motion of a ball? So we can use the de Broglie equation to show that. And all we have to do is plug in the mass of the particular electron, which is pretty small, 9.11 times 10 to the negative 31 kilograms. We plug in the velocity, which is 1 times 10 to the 7 meters per second. And if we plug this in, we get a wavelength that's pretty tiny. I mean, 7 times 10 to the negative 11 meters. Really, really tiny. Okay. If you do that for the baseball, you also get a really, really tiny wavelength. In fact, much, much tinier than the electron. All right, so what's the significance here? All right, the significance is, one, we calculated a wavelength for both. We were able to come up with a wavelength. Now, if you think of the ball and the size of the ball, the ball is pretty big compared to that 1.9 times 10 to the negative 34 meters. I mean, that's extremely tiny. So if you think of a ball traveling in sort of in the air, because you've got such a tiny, 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 tiny wavelength associated with its motion, it's pretty much not detectable at all. I mean, there's just no comparison to the diameter, let's say, of a baseball to that little tiny wavelength that we're talking about. It's moving in, or the wave motion it has, that wavelength that it's associated with that wave motion is just extremely tiny. It's not to be detectable. So we can't really detect it. So for a macroscopic object, even though there is this very, very small wavelength associated with their motion, it's very tiny, it's undetectable. We really, just for all purposes, we can ignore it. That when you're talking about something as tiny as the electron, just extremely tiny, this wavelength is actually pretty significant. So, just to kind of give you a perspective, the wavelength of the electron is on the order of the spacing between the atoms in a typical crystal. So, I mean, the electron is tiny compared to the size of the atom. So obviously here, that wavelength is going to become pretty significant in comparison to the size of the electron. And so we will see electrons have these wave-like behaviors, and that's very important when we talk about the quantum mechanical model, because electrons, yes, they're particles. We can think of an electron as one particle, but the behavior they exhibit in atoms is very strange sometimes, and that strangeness can often be correlated or attributed to its wave-like behavior. So that's going to be something that you should keep in mind when you're thinking of an electron. When you see it doing strange things, you